welcome to all. The topic of our discussion is real analysis. Now, what is analysis? Analysis is the detailed examination of the elements or structure of something. It is a systematic examination of more complicated things so as to understand the clear picture of what they are and about their characteristics. Real analysis is the rigorous study with focus on the qualitative and quantitative behavior of real numbers and real functions. Now, why do we learn real analysis? So, we get a clear understanding of what are real numbers, what numbers are called real numbers, what are real numbers, are integers real numbers, are natural numbers real numbers, and so on. What is the smallest positive real number? So, these questions seem to be very abstract, but we will be getting a clear picture of what they are by learning the subject called real analysis. Is there any such smallest positive real number existing? Is 1 greater than 0? So, these are some of the abstract questions that comes to the people's mind when they learn mathematics. Does negative numbers have square root? And so on. For a small illustration, let us see an infinite series is given 1 plus half plus 1 by 4 plus 1 by 8 plus etc. We can see that they all add up to the number 2. Let us see how. Suppose we have S is equal to this sum, say 1 plus half plus 1 by 4 plus 1 by 8 plus etc. Suppose we multiply this entire S by the number 2, we get 2S is equal to 2 plus 1 plus 1 by 2 plus 1 by 4 plus etc., which we can see that this section 1 plus half plus 1 by 4 plus etc. is the same as your S, and so we can write this as an equation 2S is equal to 2 plus S. So, this on simplification gives us S is equal to 2. So, we can see that the small fractions which we had in our mind that they are very small numbers all add up to get the number 1, because we are getting 1 plus half plus 1 by 4 plus 1 by 8 plus etc. is equal to 2, we have seen. But if we do the same procedure for the next series that we are taking, say for example, if we take the series S is equal to 1 plus 2 plus 4 plus 8 plus etc. and apply the same technique that we have done here, let S is equal to 1 plus 2 plus 4 plus etc. What is 2S? 2S is equal to 2 plus 4 plus 8 plus etc. Therefore, S we can write as 1 plus 2S. So, which on simplification gives us S is equal to negative 1. So, we can see that we are adding 1, 2, 4 and so on. They are all numbers which are positive. So, all these positive numbers adds together to get a very large number. But ultimately what we are getting is we have got a result S is equal to negative 1. So, the same technique cannot be applied in both the cases. So, why is such a discrepancy occurring? We will get a solution after we learn real analysis. Again, another example which I would like to introduce to you is, suppose we have a matrix of or arrangement of numbers, say 1, 0, 0, etc. The second row is 0, negative 1, 1, 0, etc. 0, 0, negative 1, 1, 0, 0, etc. and it goes on like this. We will be getting a pattern like this. We will be having 0, 0, 0, 1, negative 1, 0, 0 and so on. Now, let us see whether summation I equal to 1 to infinity, summation j equal to 1 to infinity, aij is exactly equal to aij is equal to summation j equal to 1 to infinity, summation I equal to 1 to infinity aij or not. Let us see. That means we will add the rows first and then we add all those row values, and we will add all the columns first and then we add all the column values. So, the first row adds to give you the value 1, the second row adds to give you the value 0, because here you are having a negative 1, then a positive 1 and all the other entries are zeros. Again this row sum is equal to 0, and if you add all these row sums, you are getting the sum as 1. Whereas, if we add this column, you are getting the value 1, this column you are getting the value negative 1, again this column you will be getting 0, 0 because the negative 1 is somewhere here and so on. So, if you add all these rows together, you are getting a value 0. So, we can see that this is not exactly the same. So, in effect we can see summation I and summation j cannot be interchanged. So, why is all this happening? We will be getting a solution after we learn real analysis. Then, so we have to study something called infinite sum and sum of infinite series to find the solution of all these questions. Now, in order to learn real analysis, we need some preliminary concepts which we have studied in the field of mathematics, which are familiar to all of you, namely sets. A set is a well defined collection of objects, and the points of the elements or the points or elements or objects of the sets, these are all the same these all have the same meaning. They are the elements of the set which are also called objects or members of a set. They are all synonymous terms, and sets are usually denoted by capital letters, whereas the elements are represented by small letters. There are two representations of set. One is called the roster form, in which the elements are listed using commas and inside a bracket. Example 1, 3, 7, 21, 2, 6, 14, 42 and so on. These are some of the elements that we have listed here, in order to show that the elements need not be in an ascending order or a descending order in a set. It can be arranged in any order. The next is the representation is set builder form, in which we will be representing the elements of the set using a fixed rule. For example, the set V is the set of all x such that x is a vowel in English, and this itself is self-explanatory, because we can understand that the set V consists of all the elements A, E, I, O and U. Then there are different types of sets. The first type is what is called the empty set or the null set, which does not contain any element. It is denoted by the Greek letter phi, and we say that two sets are equal if they have exactly the same elements. If two sets have the same number of elements, we will call them equivalent sets, whereas if the elements are the same, then the sets are said to be equal sets. Otherwise, the sets are said to be unequal, and we write A is not equal to B. Then we have subset. A set A is said to be a subset of a set B if every element of A is indirectly an element of the set B. In other words, if whenever A belongs to A, then A belongs to B. And if A is a subset of B and A is not equal to B, then we will say that A is called a proper subset of B and B is called a superset of A, because there is at least one element in B which is not in A. Then we have a power set which consists of all the subsets of the set A. Suppose we have a set A is equal to, we will show an example. Suppose we have a set A which is equal to, say, the set 1, 2, 3, then the power set of A will consist of the empty set, the singleton sets, set 1, set 2, set 3, then set 1, 2, all the sets of 2 elements 2, 3, 1, 3 and the set 1, 2, 3. In the coming sessions, we will be discussing the number of elements in the power set of a set. It is usually denoted by P of A. Then we have the universal set which includes all the elements, that is called, the entire set is called the universal set. It is usually denoted by U or X, but in our course, in the course of real analysis, our universal set is by default the set of all real numbers R. Then we need a bit of logic also for a clear understanding of real analysis. The first or the most important connective in logic that we need is the implication statement. The statement P in an implication, P implies Q, is called its hypothesis or premise or antecedent, and Q is called the conclusion or consequence. It is read as P implies Q or P only if Q. That means we need the existence of P in order to show that the existence of Q. Q if P or Q provided that P. Implication is also called a conditional statement. Then we need what is called a biconditional statement. The conditional statement, biconditional statement P if and only if Q is the combination of both the implication statements, that is P implies Q as well as Q implies P. So, it is true if and only if both P and Q are having the same truth value. That means both P and Q are true, it is true, or both P and Q are false also, this is true. It is sometimes abbreviated as P IFF Q. So, this actually is an equivalence condition. P and Q are having the same truth value. So, in this statement we have seen a conditional statement is P implies Q. So, in order to show that, or in order to prove a result if P then Q, it is easy to show in the counter direction as well. That means negation Q implies negation P. So, in order to show that P implies Q, we can even show that negation of Q implies negation of P. That means we have to first assume that Q is not true, then P is not true, then it is enough to show that P implies Q. So, that is also another way of showing that P implies Q. Okay. Now, we can move on to the introduction of real analysis, real numbers. Now, in order to introduce real numbers, first we need the number system, the set of all natural numbers, which is equal to the set 1, 2, 3, etc., which does not have a proper definition in mathematics, but in some textbooks like in Terence Tao, we can see using an increment operation the definition is given. Then we can have an integers. Integers is the set of all numbers of the form 1, 2, etc. That means the set of all natural numbers. the set of all negative natural numbers and 0. So, Z can be considered as n union minus n union set 0. So, that is the set of all integers. Now, in this session, we will be discussing what are the properties of natural numbers. So, the first and the important property, most important property of natural numbers is the well ordering property, which states that every non-empty subset of n has a least element. Say for example, we can see a subset of natural numbers, say the set of all even natural numbers. If you take the set of all even natural numbers, we can see it starts with the number 2. So, this has the least element 2, which is the least element here, that is 2. Then the set of all prime numbers, if we take, again we can see 2, 3, 5, 7, etc. These are prime numbers. Again a subset of natural numbers, again we can see that 2 is the least number there. The set of all odd natural numbers, if we take, we will be getting 1, 3, 5, 7, etc., where 1 is the least number there. So, you take any subset of natural numbers which is a non-empty subset, we can see there is a least number. That is why it is called a well ordering property, and that is why the natural numbers are written in the ascending order. So, in a more mathematical sense, we can define the well ordering property as if S is not equal to phi is a subset of n, there exists an m such that m is less than or equal to k for every k belonging to S. We require this property for the proof of many other results that follows. Now we can show that there is no natural number between say n and n plus 1. That means, why we are arranging the natural numbers in such a way that n is followed by n plus 1. How did we know that there are no natural number between n and n plus 1? So, there is a proof for that. We can see, first we will show there is no integer k lying between 0 and 1. So, if possible, let us assume. So, in order to show that something is not true, we will assume the contrary, that is known as the contrapositive method. So, let A is equal to the set of all integers such that 0 is less than k less than 1, and assume that A is not equal to 5. That means, we are assuming that if possible there exists at least one integer between 0 and 1. So, an integer between 0 and 1 means it is definitely a positive integer. So, positive integer means it is a natural number. So, A is not equal to null set means now A becomes a non-empty subset of the set of all natural numbers n. So, we can apply well ordering property, and therefore, it contains a unique least element, say m. Now, where is m located? Between 0 and 1, and m is a natural number. But we know for the numbers between 0 and 1, we will be having 0 less than m square less than m less than 1, and for a number between 0 and 1, m square is less than m. Therefore, even if m is considered to be a natural number, this should hold. So, if m square is less than m less than 1, square of an integer is always an integer, and so m square is also an integer, but m square is less than m means m is not the least integer in A. So, we arrive at a contradiction, and so A should be equal to empty set, and hence we can say that no such number exists between 0 and 1. No such natural number exists between 0 and 1. Now, we move on to our problem. We have to show that there exists no natural number between n and n plus 1. So, if possible, let k be a natural number between n and n plus 1, then definitely where is the position of k? Between n and n plus 1. Subtracting n throughout this inequality, we will be getting 0 less than k minus n less than 1, and definitely k and n being natural numbers, k minus n is an integer. We are not saying that k minus n is a natural number, but we can claim that k minus n is an integer. But then what happens? There exists an integer between 0 and 1, which is a contradiction to the statement that we have just now proved. And so, we arrive at a contradiction, and hence the proof there exists no natural number between n and n plus 1. That is why we arrange the natural numbers in the increasing order. 2 comes after 1, 3 comes after 2, and so on. Now, we move on to the second most important property of the set of all natural numbers, which is called the principle of mathematical induction. Let S be a subset of n which has the following properties. 1 belongs to S. So, definitely S is non-empty, 1 should belong to S. For every k belonging to n, k belongs to S implies k plus 1 also belongs to S. So, 1 belongs to S. So, these two conditions combined together gives 1 is an element of S, and so 1 plus 1 belongs to S, which means 2 belongs to S. If 2 belongs to S, 2 plus 1, that is 3 belongs to S, and so on. So, finally, what do we get? S is equal to n. So, that is the principle of mathematical induction. The proof of mathematical induction is like this. So, here we have to prove that if these two conditions are satisfied for a subset S of n, then that S will be exactly equal to n. So, if possible, we assume that S is not equal to n. So, S is not equal to n means S is not a subset, S is not an equal subset of natural numbers, which means there are some natural numbers which are not in the set S. That means n minus S is a non-empty subset of natural numbers n, because we have taken the set S as a subset of n. The set S is a subset of n, this is your n, and you have taken S to be a proper subset of n, because S is not equal to n by our assumption, and therefore, there exist some elements which are here which are not in S, and therefore, n minus S is not equal to null set, but n minus S is a subset of the set of all natural numbers. So, it is a non-empty subset of n. Therefore, we can apply well ordering property to n minus S, and so by well ordering property, it has a least element, say m. So, m is an least element in n minus S. So, this has a least element, say m belongs to n minus S. So, where does m minus 1 belong to? M minus 1 is not in n minus S, because m is the least. It is the least element. So, m minus 1 does not belong to n minus S. So, m minus 1 should be somewhere here inside S, because m minus 1 is not in n minus S, means it should belong to S. So, m minus 1 belongs to S means by the second condition given, if m minus 1 belongs to S, m minus 1 plus 1 also belongs to S, because we have the condition that for every natural number, if that natural number is in S, then the next natural number is also in S. And so, if m minus 1 belongs to S, m also should belong to S. So, we arrive at a contradiction. Therefore, we have S is equal to n. So, that is the proof of the principle of mathematical induction. Now, a common version of the principle of mathematical induction is, for each n element of n, Let P of n be a statement about the natural number n. Suppose that P of 1 is true. For every k belonging to n, P of k is true implies P of k plus 1 is true. Then it is true for all n element of n. Again, we have taken the case for n equal to 1 first. Then if for n equal to 1 it is true, for n equal to 1 plus 1, that means for P of 2 is true, and if P of 2 is true, P of 3 is true, and so on. So, that means P of n is true for every natural number n belonging to n. This is called the most common form of principle of mathematical induction. Then we have a second version of principle of mathematical induction, which states that let n naught be a fixed natural number and P of n be a statement for each n belonging to n, where n is greater than or equal to n naught. Suppose P of n naught is true, and for every natural number k starting from n naught, P of k is true implies P of k plus 1 is true, then it is true for all n greater than or equal to n naught. So, this is applicable for those cases for which the result is true starting from some natural number, say 3 or 4 or 10 or 100 or whatever it be. From that number on to infinity, if that result is true, we can apply this type of principle of mathematical induction. The proof of this is also quite simple. Suppose that we take the set S is equal to the set of all the natural numbers n for which P of n is true, then since by condition number 1 we are given P of n naught is true, therefore, n naught definitely belongs to S. And by the second assumption, if n naught belongs to S or if P of n naught is true, implies P of n naught plus 1 is true. Therefore, n naught belongs to S means n naught plus 1 belongs to S. And if n naught plus 1 belongs to S, n naught plus 2 belongs to S, and so on, and therefore, S is equal to the set of all elements starting from n naught, n naught plus 1, and so on. That means, the result is true for every n greater than or equal to n naught. So, that is the proof of the principle of mathematical induction second version. Now, we have another form which is called the principle of strong induction, which is a bit more stronger version of mathematical induction, which states that if S is a subset of the set of all natural numbers such that 1 belongs to S, and for every k sweeping from 1 up to k we have a subset contained in S, then k plus 1 is in S. So, that means if 1 belongs to S, singleton set 1 is contained in S, and therefore, the set 2 is an element of S by the second condition. And if we have set 1 2 is contained in S, 3 is an element of S. If we have set 1 2 3 is contained in S, 4 belongs to S, and so on, and therefore, ultimately we get S is equal to n. So, we have discussed principle of mathematical induction and well ordering property of the set of all natural numbers. The principle of strong induction also we have discussed, and in the next sessions we will be discussing more on principle of mathematical induction and natural numbers, countable sets, finite sets, and so on, and we will learn more about real analysis. Thank you.